All right, so let's talk about the defense, deep neural rejection, which is not only a good defense, but also a great name. So what you do here is you start with a model trained to do one of these things, like sort the digits, recognize handwritten digits. And then after you got your whole model ready and trained up where it's doing the sorting, now you add more neurons on the side. You take some levels of processing. And this is what I was saying before. You have the input image, and then you have multiple levels. And in very loose, approximate terms, one of these levels does something like enhanced contrast, and one does sort it into this and that. You can sort of sometimes say what these levels are doing, like for large learning models. The first one's encoding the data. The next one is looking for the meanings of the words within the sentences. The next one is looking for larger range patterns in the paragraphs and stuff. In general terms, because I think LLMs have like 1024 layers or something. In general terms, you can sort of describe what some of these are doing. But anyway, you pick some of these, like the ones towards the end, that hopefully have pretty much got things worked out. And then you generate some kind of measure of the average statistic measuring something about this image. And then you combine them and you make a probability distribution with some parameter, which is how much signal you're getting out of these layers. And now you notice things that are far from the average here, and you throw them away. This is where you just look at the image and say, does this image look funny? This image looks screwed up. It's probably been poisoned, throw it away. So you train your deep neural rejector to reject the ones that look funny. And this works. And it is sort of intuitive, because as you saw, the poisoning consists of adding little dots all over the place like snow that probably shouldn't be there. A human could pretty easily tell those poisoned images from the good images. And so that's what you do. You can train this thing up. Well, you download a pre-trained image, a pre-trained model, and here's the images, and here it is sorting them, here, images, same digits with correct values. Then you can view the predictions of the unprotected model. And it took me a week to figure this out. The person who wrote the paper and wrote the test code did not show that it worked in any way that I could understand. They had some weird graph at the end, which seemed to show it wasn't working at all. And he said, there, it works. And I'm like, I'm baffled by your graph. So I found another way to do it, which makes a lot more sense to me. So here's the predictions of the unprotected model. Here's the thing we saw before, the unprotected, here's categories 0 through 9. So the right answer is 0, and the image number, the predicted classification, and the correct classification. So this is image 0, the right answer is 7, and it predicts 7. Here's the raw output of the model, and as you can see, 7 is plus 5,005, and the rest are mostly negative or near 0, so it's strongly predicted that 7 is the winner, and on they go. You can see it got a lot of these right. This is 1, it predicted 1. The model is very good at sorting. It got this one wrong. It should have been a 5, but it predicted a 3. And I guess it should have been a 3, but it predicted a 5. Here's the 5 having the higher number than 3. And you see they're very close, 730 and 712. So that's like before. It's not perfect, but it's pretty good. And some of the images, even the original images, are confusing enough that the model has trouble identifying them. So that accuracy is not 100%. Now we can attack it with an evasion attack like we did before. We run C attack evasion PGD-EXP, which is one of the mathematical algorithms to figure out exactly which dots to change to poison it. And so you run the attack, and here's the poisoned images, which you can see they've got this snow on them now, and it's going to get them all wrong. The attack succeeds. 20 evasion images are shown here. I've poisoned the first 20 images by putting a little snow, and all 20 of them are wrong now. Correct, predicted, every single one of them is wrong. So the poisoning is 100% effective. It fooled the model every time. And now I add the deep neural rejection to it, which is what this does. And then you can choose to set the threshold. Remember, it boils all this thing down to one number, which is how funny your image looks. And you can set the threshold here, so you're going to reject 10% of the original training images. Now, they're still used to train the classifier, but the deep neural rejector is saying, those 10% are funny looking. I'm not going to take test images that look that funny. This you can adjust, of course, but that trains it on 10%. And now you can show the model how it classifies the first 20 images. And here you can make the attack images. Do the same thing. You run the same attack, C attack evasion PGDX, on the complete model, including DNR. The attack uses the whole neural net to figure out how to poison it. So you run the same attack with complete information, including the information about DNR, and even so, it fails now. The -1s are ones it rejected. So the 7 would have fooled it, but instead it rejected it. So that's not a failure. And see, a bunch of them now have -1s as the prediction, which should only go from 0 to 9. So the end result is now it only got fooled 6 times instead of 20. And the rest it rejected. So that is the defense working, as far as I can tell. And it's a nice, easy way to see that it works. If you look at the original research paper and code, there is some baffling graph at the end, which didn't make this clear to me at all. So anyway, I was very pleased to get that working, and there's various variations of this you can run to find some flags. Try rejecting 50% instead of 10%. Try rejecting 2%, see how well that works, and on you go. Then try doing a fast attack where you don't do as many cycles to perfect the attack, and see how good that works. There are lots of fun things to try here. So that's what I wanted to show you. That's as close as we get into security. These are the attacks, there's the defense, and all this stuff is in its infancy, like the pre-beta level. So we're getting in the early days. All this will change greatly as we go ahead. But I think it's real valuable to learn what you can as fast as you can, because this stuff is really powerful. And it's really poorly understood. So, all right, that's what I wanted to show you. I'm going to stop this video.